Hey, everybody, this is Larry. This is July 13th, the 13th day of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's farm. So my setup is from a different room, and I'm trying these AirPods instead of my usual mic setup. So let me know what you think about the sound quality and stuff like that. Yeah, it'll just be very helpful if you can leave a comment about if the sound quality is good or I need to figure out what to do. But yeah, hit today's farm is find peak element. So peak element is one that's strictly greater than its name is. Find a peak element and return its index. If there are multiple of them, return index of any of these peaks. Okay. So yeah. Hmm. So the linear time one is going to be obvious. You just go from left to right, right? And that's kind of that's good. But we want to apparently do this in log n time. So with log n time, one of the things that we have to do is that it can be at any of the peaks. So I think we have to figure out an invariant that we can kind of search by or something, right? And to be honest, a little bit cheating, a little bit meta is that when you see something like log n, it's first thing that I would think about is binary search or ternary search or something like that. And in this particular problem, let's see. So n is 1,000. You don't actually, honestly, also if I saw n is equal to 1,000, I would not use log n, but I guess it wouldn't matter that much because for any reasonable n that we can actually read the input of, we wouldn't do it in log n anyway. But in any case, let's see. So core part about these problems is try to figure out invariant or some kind of property that you could search on, right? And the first thing that I would think about is let's see. How would I think about our log n, right? Well, well. The thing that I would think about, and I have a couple of variations. That's what I'm actually thinking about, even though I'm not honestly articulating it that well. Maybe it's a setup, but the idea that I'm thinking about is just no. So you have, say you have this array, and let's say you're playing around with a binary search type idea, right? Of course, this is not binary search because there's no ordering, but the thing is that you only need to return one of the peaks, so you don't have to. As long as it's a peak, it's okay, right? So here we look, right? Well, what does it mean when I have here, in the middle, but what I'm going to do is compare it to the edges, which is left and right. And here, I guess the first thing you can also do is just check if the left is a peak and if the right is a peak. If not, then here we can take the max of the three numbers, maybe. Yeah, maybe. I said maybe. Yeah, because then as long as you have some way to remove half of the array every time, and you're guaranteed that in the half that you did not remove, in the half that you keep, there is a peak in there somehow, that should be good enough. So I think in this case, it, so maybe there are a couple of scenarios we could iterate or enumerate through them. Some of them are just symmetry, but let's say we have this case where 1, 3, and 4 at the peaks. Well, in this case, we can throw away the left because we know that, well, at worst, we know that 4 is a potential peak. I know that it's not an actual peak, but at the worst, it is at least a potential peak because the local maximum is there, right? Um, and then okay, well maybe you don't even. Yeah, I mean, I think there are a couple of ways you can do it, which is why I'm confusing myself and kind of thinking through it a little bit more, to be honest. Because I think you can also maybe just look at the elements that are next to it. So in this case, it could be 1, 3, and 5. I don't think it matters either way. As long as you're consistent and as long as your reasoning makes sense, then that's okay. And here, what I'm saying is that 3 and 4, we know that the peak is going to be inside because either 4 is the peak, and if 4 is not the peak, that means that it's going to be to the left of the 4, and therefore chopping off everything to the left of the 3 is okay. Or even chopping off the 3 is probably okay as well, because you don't need the 3, because we know that it is not going to be a peak, because 3 cannot be a peak because 4 will be higher than the 3. Like even if it's like it goes 3, I mean 3 could be a peak, but you can always throw it away because there'll be another peak. Actually, maybe that's a more precise saying. But same thing here with we just look at adjacent elements, because we can see 3 and the 5. Okay, well, what happens? Well, if it's 3 and a 5, then we know that on that half, um, we can find a peak on that half because it's either the 5 or something to the right of the 5. So same idea there, and we can forward everything to the left there. And there are also variants, I think, in that you don't even have to look at the 1. You can just look. Well, maybe you can. I don't know. I mean, like I said, there are different variants, but our idea is still all the same, which is that um, if there's a way that you can throw away half the data and still have um, and still guarantee that in the half that you don't throw away, still have a peak, then that should be good enough. And here, note that there are a couple of possibilities, right? One is that if you have 3 numbers looking at 3 numbers in a row, there are only a couple of possibilities. In this case, there's 1, 3, and 5, and we already talked about it. The other case, there's 3, 5, 3, and 1, which is the same but symmetric, so we already talked about it. And then there's one where you have maybe 5, 3, 6, and 3 is at the bottom, but then in that case, it doesn't matter which way you go. Whichever way you go, there's a peak, right? So in that case, it actually doesn't even matter. And the only other case is if this is already a peak, which, well, you already have an answer. So yeah. So I think this case in this enumeration, I think that works, because I think those are all the possibilities, right? Because it's just less than, greater, greater, less than, greater, greater, and less than. So 4 possibilities and so forth. So I think now I am confident enough to kind of start working on this. And the thing that I would think about is binary search is hard, so you have to be really careful about it. But that's pretty much it. We can set the left to 0, right is equal to n, or n minus 1 to be more precise, because we want it to be inclusive, and n is the length of nums. And that's just, I'm just thinking about how to do edge cases where the peak is at the edge, keeping in mind that they're negative infinity. So yeah, so I think I'll just check in the beginning really quick so that I don't have to think about this possibility later. Yeah, if num sub 0 is greater than num sub 1, does it always have it could have one element, which is actually awkward. If it's one element, then no, I was thinking about the other way of doing it, and I think I'm going to do it the other way instead, where I just take nums and then I add, negative infinity, and I'm just looking at the range of number, negative infinity on both sides. And you want your negative infinity to be a number that's smaller than this, or bigger than it, or more negative than it. So yeah, so this is going to be good enough. Okay. Then now I don't have to worry about this case anymore. Do I have to adjust my left and the right inclusive to be this? No, what n? No, it's n minus 2. Yeah. So I have to worry a little bit about maybe rounding, but yeah, in this case, again, I've done a lot of binary search videos, so I'm not going to go into super details, but the idea between this one isn't a true false binary search. It's just basically what we said, right? So I'll repeat it in a second, but here, you may see different ways of writing about it, and it just depends on whether your left, right are inclusive or exclusive. For me, I generally keep them inclusive. So I write it like this because when they're inclusive, when you have one element inside the range, that's when left is equal to right, and when left is equal to right, that's when this terminates, right? So yeah. So then let's do mid is equal to left plus right over 2. Let's also check really quick that middle is, if middle is greater than, is it strictly greater than? Strictly greater, okay. Um, Mid minus 1 and num submit is greater than num submit plus 1, then we return mid. I actually skipped the thing that I said I would do, which is to skip the to check the corners. But the thing was that now that we added to infinity and we don't count it, we should be okay. Even though I guess it would be a little bit faster, but it should be fine. And then we also think about one number situation, but that's okay. We'll test the one number case in a second. But before that, what I'm doing now is I add it so I don't forget because I forget a lot. Memory, my attention slash working memory isn't what it used to be. Okay, okay, so now we know that that's mid. Okay, and then now we have two cases. It doesn't really matter, but if this in this case, that means that, what does this mean? This means that to the left there will exist at least a peak, at least one peak, so we can keep that side, the left, right? So that's basically the idea here. And what that means is that also, I'm just thinking really quick. What if they're equal? I guess if they're equal, what if there are no peaks then? If they're equal, oh, okay. So that's what I was looking for because you can imagine just a flat plateau, and then in that case, I was just trying to figure out what the answer is. But apparently they're addressed in the constraints instead of in the problem for some reason. Okay, fine. So that's not a possible case then. Then let's move on. Yeah, here we set the right is equal to mid minus 1 because this is inclusive. And you can actually also do right is equal to mid, but it doesn't really matter. I think in this case, you want this because you want to exclude num sub mid because you know that that cannot be a peak, right? And else if num sub mid plus 1 is greater than num sub mid is the same idea. Left is equal to mid plus 1. Mm, is is that sufficient? I'm trying to think what is the only other else case. I don't think there is. I don't. I'm just going through in my mind really quick. So if num submit is already a peak, then we already return it. Otherwise, one of the two has to be greater than it. So I think this is. I mean, we could. Uh, I think we can translate this to else, though. This is the only case that's left, right? Um, yeah, because this is if this is greater than both of them. If this is, that means that if this is not the case, then one of these two have to be true. Yep. Okay. Um, and that's really it. I think conceptually, the one thing that I would say that is rarer for this one is that you have to think about the off by ones. And I'm honestly not quite sure about this one. That is one thing that I may be a little bit more weak at. So maybe in this case, I'll set right is equal to mid so that so this will induce it to round up and this will induce this to round down and that kind of cancels out. And then at the end we just return left. It doesn't. You also return right. It doesn't really matter because they should be the same. But yeah. Okay. Oh, wait. Oh, yeah. I mean, this is because we added the infinity index, so now we have to kind of -1 to re-index it to the original index, if you will. Hmm. Did I mess something up? How is this right then? Did I? Okay, let's double check this for a second. Hmm. I see, I see. Whoops. Because I have the other place of returning, which is here. So I have to return my mid -1 here as well. I think that's fine. Because I was just like, usually I write this in a, I don't early terminate on my binary search, so I didn't know to look for it. But that's why you test your code because sometimes things are a little bit different. Okay. So let's see. Am I good? Dun, dun, dun. Yeah, okay. Let's give it a submit then. Maybe I'm okay. Hopefully this is good. Yep. Okay, cool. And looking through this code is obviously log n because we just every iteration through this loop, um, you have this range and it gets chopped off by half, and it takes log n time to chop it all the way to termination. Um, yeah, that's pretty much all I have. I know that I'm a little bit slow on this one and maybe deliberate in my explanation. Hopefully hopefully this was educational though, because I do go over all the thought processes. I go through them. I haven't seen this. I feel like I've seen a similar problem, but everything feels like similar problem to me at this point, to be honest. Um, at least at this level. So yeah, let me know what you think. Hit the like button, hit the subscribe button. Join me on Discord. Hope you enjoy it, and remember, let me know about the sound quality. Stay good, stay healthy, stay cool, and I will see you later. Bye bye.